Today we'll continue to discuss hidden Markov models and expectation maximization, and we'll use that as a segue to briefly discuss probabilistic programming. So the example we're going to discuss is a hidden Markov model, where the Markov chain starts in state 0 or 1 with probability a half each, and then moves according to a transition matrix of the form Q, 1 minus Q, 1 minus Q, Q. So that means the Markov chain always stays in its current state with probability Q, and transitions to the other state with probability 1 minus Q, regardless of which state it's in. So this is not a fully general 2x2 transition matrix, but to keep the number of parameters reasonable, we're just going to assume that the staying probability is the same for both states. So the parameter Q here is the stickiness of the Markov chain. If it's close to 1, then the Markov chain tends to stay where it is for long stretches of time between switches to the opposite state, and if it's low, then it tends to switch rapidly. Now the model we're considering is a hidden Markov model, meaning that this sequence Z1, Z2, and so on of Markov chain states is not going to be what we actually observe. The model is going to add some noise to each of these Z states to give us an X value that's going to correspond to the actual data we're going to see. And we'll assume that this noise takes the form of adding a Gaussian with unknown variance sigma squared. So these Gaussian random variables being added to each Z are independent of each other and independent of the randomness that generates the Markov chain. So what we're going to actually observe is this sequence of X values. And our goals will be to try to say something about this underlying sequence of Z values, as well as these two parameters, Q and sigma. And there are various approaches we could take. For example, we could take the Bayesian perspective and treat the parameters Q and sigma squared as random variables with some prior distribution, and try to sample all of the Z's together with Q and sigma from the posterior distribution given the observed data. Alternatively, we could take a frequentist perspective and treat Q and sigma squared as fixed unknown constants and try to maximize the likelihood. And that's tricky because the Z random variables are unknown. So we could try to maximize the likelihood directly over the X's, but that turns out to be computationally intractable because of the difficulty of writing down the likelihood with no Z's. But expectation maximization gives us a way out. It says pretend that you know the Z values, work out the likelihood over the X's and Z's, then take the log, then take the expectation, and then try to maximize that. So we'll take the expectation maximization approach first, and then we'll talk about the Bayesian approach next. So first, let's visualize both Z and X with their graphs. This is an example of a fairly sticky Markov chain with a Q value of 0.8 and a variance value of 0.5 for the noise. So we define an offset array here. That's an array that's indexed by something other than 1 to the number of rows and 1 to the number of columns. And specifically here we'll use axis indices of 0, 1, and 0, 1. So we'll write a function to generate from our transition matrix, and we get an example trajectory that looks something like this. So it stays where it is for long stretches, but it does switch a significant amount as well. And then to each value, either 0 or 1, we add a Gaussian with a variance equal to sigma squared, with a variance of 0.5, and we get a corrupted signal that looks something like this. So you can imagine that if you needed to guess just based on visual cues, you could detect things like this shelf here, which show up in the form of the values being relatively high on average for this long period. But you can't tell for sure whether it took a dip down for a couple of steps. You can only guess broadly what it's doing. In other words, the conditional distribution of the Z's of this blue graph, given the observed X's, this orange graph, is not deterministic. There's some conditional probability mass that's sort of concentrated around this kind of a state, but it also has some mass on some other nearby states. And even on very implausible states, for example, states which stay at 0 through this stretch, there's still some probability mass. It's just very small. So we'll need to think about this idea of a conditional distribution of the Z's given the X's quite a bit. So remember the general steps for expectation maximization. We'll start by finding an expression for the likelihood, which incorporates the observed X's as well as the hidden Z's. So we'll treat the Z's as known, representing them as variables, and work out the likelihood of the observed collection of X's together with any possible values for the unobserved Z's. Then we'll take the log, and then we'll take an expectation of that, where the Z's are treated as random variables whose distribution is the conditional distribution given the X's. So the X's are going to have two influences there. One is that they show up directly in the likelihood on their own, and the other is that they dictate the distribution that we take the expectation with respect to. And finally, we'll just maximize that expectation. So step 1 was to work out the likelihood over the X's and the Z's. So we'll start writing little z and little x, with the idea being that these represent constant values that we're imagining that we've observed. So the x's we will actually have observed, and the z's are variables representing constant values. So each one of these z's is going to be either a 0 or a 1. But we're leaving them as variables because we're going to want to end up considering all possible combinations of those values. So let's think about what the likelihood is for this particular combination of z's and x's. We can do that by just navigating this Bayes net. So we start here in the top left corner because that's the only root node of the diagram. And the probability that we observed z1 as our first state was 1/2, regardless of which z value, because we stipulated that this Markov chain is going to start in a uniform random state, either 0 or 1, each with probability 1/2. So here we've accounted for z1. And the probability that we see this particular z2 value here, given that we have already seen z1, is going to be q if these two values are equal, because that's the transition probability between any state and itself, or 1 minus q if they're different. So we can write that by saying q times the indicator of z2 equals z1 plus 1 minus q indicator of z2 not equal to z1. So that accounts for the contribution to the likelihood of this z value. Likewise, we'll get a similar contribution from every other z. So what we can do is just multiply this expression for every z that we see. And that takes care of all of the other zj's, from z2 up to zn. Then, conditioned on all of those z values, the probability that we would see an x value very close to this x value is proportional to the Gaussian density at x1 minus z1. And similarly, the density of this random variable that got added to z2 to give x2, evaluated at the actual observed difference x2 minus z2, is another factor which looks just like this one, except with 2 in place of 1. So accounting for all of those factors, we can just turn this 1 into a j and compute the product as j goes from 1 up to n. And this factor accounts for all of the xj's. So now we have a likelihood of the full model, and the procedure for that is very reproducible. We just navigate the Bayes net, and at every step we multiply by the conditional probability mass function given the parents of that random variable. Or if it's a continuous conditional distribution, then we multiply by the density instead of the mass. In any case, this is our likelihood, and next we'll take the log to get a log likelihood, and finally we'll turn these little z's into capital Z's, treating them as random variables, and take the expectation with respect to the conditional distribution of those random variables given the observed x's. So if we take the log, turn all the products into sums, and simplify a bit, we get an expression like this one. And then lastly, we'll capitalize all of the j's and take the expected value. Let's pause for a moment to appreciate some of these terms. So remember that q and sigma are the things that we're trying to optimize, and they show up in relatively simple form. For example, q shows up here and here, and sigma shows up here and here. So we can give a name to this quantity, maybe let's call it A, as well as this quantity, let's call it B, and this one, let's call it C. And then we can differentiate with respect to q and with respect to sigma to find the values that optimize this overall expression. And I'll skip that bit of calculus and algebra, but it turns out that the maximizing value of q is a over a plus b, and the maximizing value of sigma squared is c over n. So if we can estimate these quantities a, b, and c, this pair of formulas will give us our update rule for the expectation maximization algorithm. Because remember, the point was to find the parameter values that maximize the expected log likelihood. So let's take a look at these quantities a, b, and c and think about what they mean and how we might estimate them. So this quantity is 1 whenever we have a stay in the Markov chain sequence. In other words, the same state appearing twice in a row, and 0 otherwise. So altogether, this sum just counts the number of stays. And so overall, this expression A is saying, what's the expected number of stays in the Markov chain? Likewise, this second number is the expected number of switches. And lastly, C is the expected cumulative squared difference between the z's and x's. So let's look at these two pictures and think about which one we would guess has a larger A value. So remember, A is the expected number of times that the Markov chain stays in the same state. And what you see in this picture is that there's quite a long stretch where the values seem to be centered around 1. It looks like initially maybe the Markov chain is in state 0, and then it switches somewhere around here to state 1, and it stays there for a long time. Maybe on a few occasions making a dip downward, but then again maybe not. So we would expect this first one to have a conditional distribution on z, which has its probability mass concentrated near this path that makes one switch up and then stays constant. So we might expect this to be the mode, the sequence of z's that's most conditionally probable given the observed x's. and there would be some other paths that would also carry a decent amount of probability mass, and other states which are very incompatible with the data and will have a very small probability. So the joint distribution of the z's given the x's might be quite hard to describe directly, but it's helpful to think of it as a collection of observations, sort of like the picture we have drawn here. Like if we could sample the whole path of z's from its conditional distribution given the observed x's, then we could think of that as a way to visualize that conditional distribution. Like maybe the first observation we get happens to be the mode. Maybe the second one is 2, because the mode is pretty likely. Maybe the third one happens to go down twice. Even though that's not super likely, it does happen some. Let's say it happened that time. Then we happen to get the mode again. Then we happen to get one where it switches a little bit earlier and then makes another switch later, and so on. So we're conceiving of this complicated joint distribution over the z's, given all of the observed x's. We're just saying, well, let's say we can sample from it, make a bunch of observations from that distribution, and just kind of see them all together. Furthermore, with this conception of this joint distribution, we can pretty accurately estimate the expected value quantities we want. For example, if we want to know the expected number of switches, we just count them in each of these observations and take an average. Like here there's 1 switch, here there's 1 switch, here there are 5 switches, here there's 1, and here there's 3. So based on these 5 observations, we would come up with an estimate of 2.2 for the expected number of switches. And the name for this concept is Monte Carlo. We're estimating an expected value by simulating many observations from the random variable whose expected value we're trying to compute. So it might seem that sampling z from its conditional distribution given the x's is not an easier problem than directly computing the expectation. However, we have a trick up our sleeve, which is the Metropolis-Hastings algorithm. So we can start at some z, or maybe randomly initialized, independent at each time step, and then we just choose a position at random, propose flipping the bit in that position. So if it's a 1, pull it down to a 0. If it's a 0, push it up to a 1. And then we either accept or reject that proposal based on the likelihood at that new state. For example, let's say we chose position 3 here. We propose flipping this bit to a negative, so then it would stay for this first step and then jump up for the next step. And the probability density associated with this full combination of z's and x's is subject to a few different changes when we make that flip. For one thing, we were picking up a factor of 1 minus q here for this second step from j equals 2 to j equals 3, and now we're picking up a factor of q. Likewise, for the step afterwards, before we were staying, so that gave us a q, and now we're jumping, so that gives us a factor of 1 minus q. Furthermore, we had a Gaussian density value evaluated at this difference before, and then after we take the step down, we have this much larger difference that we're picking up a density for. So that corresponds conceptually to the idea that if x is up here, then it's more likely that z is 1 than that z is 0, all else being equal. So remember, to get the acceptance ratio, we calculate the mass or density, in this case density, at the new state, divide that by the density at our current state, and then accept the proposal with that probability. Or if that ratio is bigger than 1, then just accept it with probability 1. So we can avoid having to split off that greater than 1 case by just saying we'll accept if this uniform 0, 1 random number happens to be less than the density at the proposed set of z's and x's divided by the density at the current set of z's and x's. And notice that the vast majority of factors are going to cancel because they're the same for both. If we just change the bit in this position, then all the q's and 1 minus q's we pick up for the other parts of the z path are going to be the same at the new state and at the old state. And likewise, all of these other z minus x differences are going to be the same. So we can just account for the actual changes. And there are various ways to write that down, but conceptually we just get a q or 1 minus q difference here on the front side, another one on the back side, and then another difference for this change in the Gaussian density. So I'll write that down like this. So if zj minus 1 was not equal to zj, then after we flip, they will be equal, and that will give us a factor of q. So zj here is still the old one. We haven't flipped it yet. Alternatively, if they were equal, then after we flip, they won't be, and we'll pick up a factor of 1 minus q instead. Then we're going to pick up another product just like this one, except for the transition from zj to zj plus 1. And then finally, we pick up this new Gaussian density, which you can write as 1 over square root of 2 pi sigma squared times e to the minus xj minus 1 minus zj squared over 2 sigma squared. So 1 minus zj corresponds to the flipped bit. So if it was a 0, this is going to be 1. If it was a 1, this is going to be 0. So those are all the factors in the proposed density that change. We need to divide that by what they were in the original density. And there are lots of other factors, as we said, but we're just going to ignore those because they're going to cancel. They'll be the same in the top and the bottom, and they'll cancel. So that's a bit of an ugly mess to write down, but try not to get too worried about the way to write it down symbolically, because we can just program this using if statements, manage issues which are kind of messy in math notation, like this expression, which is really conditional. So just for concreteness, suppose this value is 1.5. Then the acceptance ratio we would get from pulling this green point down from 1 to 0 would be, for the new state, we have a factor of q, then a factor of 1 minus q. Then for the Gaussian, we would get e to the minus 1.5 squared over 2 sigma squared. And then for the old state, instead, we would have 1 minus q and q for those two factors. And then the exponential factor would be e to the minus 0.5 squared over 2 sigma squared. So actually, in this case, these factors would cancel, corresponding to the fact that we didn't actually change the number of switches when we flipped that bit. If we changed the number of switches, we would pick up a factor here that actually contributes to the acceptance ratio. So in this case, the probability of accepting this flip would be less than 1, because again, these factors cancel, and this quantity in the numerator is smaller than the quantity in the denominator. So we are going to look at one variation of Metropolis Hastings, where instead of choosing a random position to update at each step, we cycle through the positions in sequence. So we make a proposal to flip the first bit, and then we make a proposal to flip the bit for j equals 2, and then j equals 3, and so on. And each time, if we accept the proposal, we actually make that jump. We alter that path for purposes of computing the acceptance ratio for the next random variable. So let's use this interactive to visualize how Gibbs sampling works. So we're going to cycle through the z's, and for each one we're going to propose flipping it to the opposite value. And with some probability we'll accept that flip. But if the likelihood stays the same or goes up, we'll definitely accept. So you can see that most of the flips are getting rejected initially, but some of them are getting accepted. And so we're changing our state as we go. Then once we get to the end, we're just going to start back over at the beginning. And after only 1 or 2 passes, our state will still reflect some of that random initialization. But after we make sufficiently many passes through, the effect of that initial state will have worn off, and we'll be looking at a state whose distribution is approximately the correct thing. It's approximately drawn from the conditional distribution of the z's given the x's. So we can do that a few times for this particular fixed x. So x isn't changing here. You can see that the z's do change a bit. So these are just random draws from the conditional distribution of z given the x's. So you can see certain things are consistent, like it's very unlikely to make a dip in this region, and you can see that by virtue of many of the samples being pretty constant through there. But around the edges, exactly when a switch happens is a little bit random. You can see it kind of fluctuating from side to side, and occasionally you see an extra dip somewhere. It's actually changing the number of switches. So this ensemble of blue paths that we sampled here can be thought of as a representation of the conditional distribution of z given x, of the blue path given the observed orange path. So with that in hand, we can just sample many of these blue paths from its conditional distribution given the orange one, and count the number of switches. That'll estimate B for us. We can count the number of stays, which is going to be 99 minus the number of switches. That's going to estimate A. And then we can also look at all of these differences. So for each j value, we can look at a difference between the blue curve and the red curve at that value of j. We'll get 100 total deviations between blue and orange. And we can average the sum of squared deviations that we get, and that's going to give us a pretty accurate estimate of sigma squared. So we have this function estimate ABC, which was defined in this script, and it gives us some pretty reasonable estimates. We have 77.29 as our expected number of stays, 21.71 is our expected number of switches, and notice that those two numbers add to 99. And then the accumulated sum of squares is 27.15. So that means if we square sum all the differences between orange and blue, and do that for many different observations, then on average we get a value that's about 27. And if we run this again, we're going to get slightly different values. So these two will still add up to 99. They'll still be quite close to what they were before. This value likewise will be close to what it was before, but it's not exactly the same because we're using a Monte Carlo estimate. If we wanted to get more accuracy here, we would pay the computational cost to do more Monte Carlo simulations. So finally, we can run the EM algorithm and see what it does for us. So let's just briefly look at this code to see that it's not doing anything beyond what we already discussed. So the acceptance ratio computation is exactly as we described it. We have some Q and 1 minus Q factors. We compute the PDF of the normal distribution. We handle the j equals 1 and j equals n cases separately, so implicitly we were discussing j strictly between 1 and n in the middle, where you have a switch on both sides. The first one and the last one are different because there's nothing before or after, respectively. So those cases are handled separately. Otherwise, it's just doing the calculation we already discussed. So get single Gibbs sample is just performing a single Gibbs sampling pass. It's going from j from 1 to n, and for each one, it computes the acceptance ratio and then flips the bit if appropriate. And then Gibbs sampler here is just doing 75 passes, starting from a random initial state. Estimate ABC is just coming up with a collection of observations and then summing the number of stays for each one, summing the number of switches, and then finding the accumulated squared difference. And finally, the EM algorithm is just estimating A, B, and C, performing suitable updates to Q and sigma squared, and then it gives us this nice report as it progresses. So it starts at 0.5 because we programmed it that way, and then it moves up pretty close to 0.8. It's going to end up around 0.77 or 0.76. It's fairly close to the correct value of Q, or rather the value of Q that we use to simulate the data. And likewise, it's moving towards a sigma squared value pretty close to 0.25, which is the value that we use to generate these data. And we wouldn't really expect to get these values much closer because we only had 100 observations. So even if we could see the exact value of Z, we wouldn't expect a particularly great estimate of the staying probability. And likewise, you would expect a bit of error in the estimate of sigma squared due to the fact that we only have 100 observations from the normal distribution generating the noise. So this did a pretty nice job, and we got values quite close to these much earlier on, so we probably didn't need to go for 500 iterations here. But notice that it was a bit computationally expensive. Markov chain Monte Carlo has that property. We need to generate a lot of observations from this fairly complicated joint conditional distribution, and for each one of them we need to perform a large number of updates to ensure that the distribution we're drawing from is quite close to the actual limiting distribution of that Markov chain. So let's segue now into talking about the purely Bayesian approach. In some ways it's simpler because we're not distinguishing Q and sigma as special concrete values to be treated separately from the Z's. So in the discussion so far, the Z's have been random, but Q and sigma are not, and so we have to do this alternating expectation maximization procedure to take care of that. On the other hand, if we treat Q and sigma as random variables with a given prior distribution, then we can just perform these Markov chain updates, with all n plus 2 random variables getting updated on each Gibbs sampling pass. So we go through and propose flipping each bit, and we propose some change to Q and some change to sigma squared, and then make another pass through. And a nice thing about taking this Bayesian approach is it does simplify the process. If we just specify our observed data X, the structure of the model, which we can write as a program, and the procedure for forming these proposals, then the rest of it can be automated. It's computationally feasible to compute the likelihood ratio for each of these proposals and coordinate the whole process of executing the Gibbs sampling procedure. And systems which automate Bayesian inference in this way are called probabilistic programming systems. There are several popular ones, perhaps the most popular of which is called STAN. It has bindings for R and Python and Julia and other languages, and it's very performant. We're going to use a native Julia probabilistic programming language called Turing. And I don't want to get too far into the details of this, because in practice you'll probably use the probabilistic programming system that best integrates with your other tools. But I do want to show the simplicity of these systems and what's possible to do with them. So the way Turing works is that you use a macro called model to define a new model. So other than this macro call, it looks very similar to a function definition. You give it a name, and then the parameter is going to be the value that's actually observed. So here we have x for a vector of x values that we're going to be able to supply observed data for. The other random variables are going to be specified in the body, and the package is going to be responsible for keeping up with them. So we're going to pick up our n value from x, just however many components x has. And then z is going to be a vector of the same length, and it's going to consist of integers because it can only take the values 0 and 1. So as a slight idiosyncrasy of this package, this does have to be t-zeros rather than zeros. That gives us a slightly different type of array that Turing is set up to handle. But then we just specify our prior distributions and the structure of the model in plain code. So we say our prior on Q is, let's say, uniform from 0 to 1. So we're trying to be agnostic there. Sigma squared is inverse gamma with these very small parameters, 10 to the minus 3 and 10 to the minus 3. So again, we're trying to not be super opinionated about what we think sigma squared is going to be. Then we define our P matrix just as we did before. So that's array indexed by 0 and 1 along each axis. And it's just a Q staying probability and a 1 minus Q switching probability for each state. Z1 is going to be randomly chosen from 0 to 1. With probabilities given by 0.5 for each. So discrete non-parametric is the distribution's name for a discrete distribution where we're going to explicitly specify the possible values and the probabilities for each of those values. So x1 is going to be normal with mean z1 and variance sigma squared. So that was specified in the model. We said that we're going to add to z1 a normal random variable with mean 0 and variance sigma squared. So in the end, x1 has a mean of z1 and a variance of sigma squared. And then we just loop through to fill out the rest of the Bayes net. For each I from 2 to n, we take zi and draw it from another discrete non-parametric distribution with possible values 0 and 1, and whose probabilities are given by the appropriate row of P. So if the previous step was 0, we're going to be pulling from the first row, and if the previous step was 1, we'll be pulling from the second row. And then after we have each z, we can say that the corresponding x is drawn from a normal distribution with that mean and the specified variance. And then that's it. We don't have to return anything. We've just told the package implicitly what all the intermediate parameters are, so q, sigma, and all the z's. So it's going to work through the body of this function and find all of those things. Basically everything that shows up before a tilde. And it knows that the data x are the observed data that it's going to have to use to perform inference. So it's going to make some random initial guess behind the scenes for each unknown random variable, q, sigma, and all the z's. And then it's going to perform a large number of updates where it proposes changing each one and accepts or rejects with appropriate probability. If you run that for a long time, then you'll be sampling all the z's and q and sigma from their joint conditional distribution given the observed x's. So we do have to tell the system what samplers to use, and we're going to use a Gibbs sampler as we discussed because we have all these z's to loop through and q and sigma. Furthermore, the z's are discrete, so we'll have to propose switches to them in a different way than q and sigma squared. And we could just use plain vanilla samplers here, but I just want to mention a couple of more advanced samplers that are very common to use because they tend to be much faster than a naive Metropolis Hastings that just uses something like a Gaussian proposal distribution. So the first is called Hamiltonian Monte Carlo, and roughly speaking, the idea that you want to have in your head is just this picture, which is that in very high dimensions, you might have probability mass sort of concentrated along a particular lower dimensional surface. And then if you make Gaussian proposal steps, many of those steps often take you directly away from that surface where the density is very small, and you'll have a very small probability of accepting that jump. And you'll have to wait quite a while before you see a jump which happens to point in the correct direction, along which there's a significant amount of probability mass, and then you might accept that jump. But then there, you'll again take many false starts out into the directions where the density is low, and then you'll happen to take a good step again, and maybe you'll step back this way, but only a few of your steps are actually giving you good traction to move around within the space where there's a decent amount of probability mass, and it ends up taking a very, very long time to converge. Although we won't cover the details, Hamiltonian Monte Carlo is a technique that uses autodiff on this density function and uses that to figure out what the good directions are. So it's making proposals that are F-aware in such a way that you get the appropriate limiting distribution, but you don't waste all this time taking lots of steps that are very likely to be rejected. However, because Hamiltonian Monte Carlo involves differentiating a density, it's not suitable for discrete variables. So for those, you need another type of sampling method. You could just propose flipping the bit in this case, but instead we'll talk about something called particle Gibbs, which actually uses several instances of each random variable at the same time and uses that ensemble of particles to make a decision about whether to accept or reject. So we set up our samplers here. We'll define a Hamiltonian Monte Carlo sampler, and these are parameters. This one is epsilon, which is the step size, and 10 here is something called the leapfrog parameter, and I'll leave you to get into the details of that elsewhere if you like. But we're telling the sampler that it should deal with q and sigma squared. And here we define a particle Gibbs sampler with 20 particles, and we're telling it to work on the z random variables. And then we package those together with a Gibbs sampler that's going to apply Hamiltonian Monte Carlo on these two and particle Gibbs on all of the z's, and it's going to alternate through the random variables performing these updates. And then to actually perform those updates, we just need to call the sample function on our model called on the observed data. So capital X here is storing the actual observed data, and when we call sample on this thing, it's going to generate a specified number of random observations of the hidden random variables given these observed x's. So it's going to use this sampler G that we specified, and it's going to make 10 Markov chains. And it's going to return them in an object that contains information about those runs. And actually, let's do 50 of these. So it knows what all the hidden random variables are. It finds the Q, all the Z's, and also sigma squared is listed here. And it does 50 iterations, and it gives you some summary statistics for each variable, indicating the values that it got over those 50 iterations. For example, Q has a mean of about 74% with a standard deviation of about 0.05. Some of the Z's never changed, like Z6 and Z7 were always zeros for all 50 iterations, so there's a standard error here of 0. And sigma squared is estimated to be about 0.69. We also have quantile information. We can get a glimpse at the distribution of each of these. For example, Q is seldom below 0.62 and seldom above 0.83. And if we wanted to see a histogram of the Q values, we can extract all 50 Q values with this getParams function. And we can make a histogram of that if we want. We see these values between 0.6 and 0.85, and it's sort of concentrated around 0.75, maybe a little bit less. So in summary, to estimate Q and sigma squared for a hidden Markov model with a state space of 0, 1, a staying probability of Q and a switching probability of 1 minus Q, and a normally distributed error with mean 0 and variance sigma squared, we talked about a couple of different approaches, which involves computing expected log likelihood with respect to x and z, substituting for x its observed values, and dealing with the z's by taking the expectation of the log likelihood with respect to their conditional distribution given the x's. Then we choose Q and sigma squared to maximize that value and update them. And then we just alternate back and forth between these two steps, recomputing expected log likelihood and then maximizing and updating the parameters. And the methods we learned along the way are that when we wanted to work out the log likelihood, we just navigated the Bayes net. And every time we want to deal with a new node, we just multiply by the probability mass or probability density for the value in that node with respect to the conditional distribution given the parents of that node. And then also when we wanted to compute this expectation, we used Monte Carlo. So we started with some path of z's, and then swept through accepting or rejecting updates in each position, until eventually we've run it long enough that the distribution of this path accurately reflects the conditional distribution of z given the observed x's. And then we do that repeatedly, and use this ensemble of observations from the desired distribution to approximate the expectations that come up in this expected log likelihood formula. And then the second approach was Bayesian, which involves treating the Q's and sigmas like random variables just like the Z's, and then doing the whole thing with these Markov chain updates. And we saw that this second process can be handled in a way that hides all of these log likelihood calculations using probabilistic programming.